How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at 5.5 problems which address calorimetry. So the first one is going to be, what are the units of heat capacity? So remember, heat capacity is that big C, which is going to be the amount of heat that results in a change in temperature, so degrees Celsius, right? So the units on that are joules per degree Celsius. And this, again, big C is for the whole system. Whereas if I'm talking about specific heat, which is different, it has little c, that is going to be for just a substance. So if we're talking about temperature change of a substance, then we have little c, which is for specific heat. And if we're talking about a whole system, then we go to heat capacity, which has the units of joules per degree Celsius. Or specific heat, again, it's going to have to be joules per grams degrees Celsius, because it depends on how much of that substance is there. It's not talking about the whole system, it's talking about a specific substance. 18 says, what are the units for specific heat? Well, I just kind of gave that one away, didn't I? Specific heat is going to be the joules per gram degrees Celsius, because it depends on how much stuff there is. If you have more stuff, then the temperature change is going to be less. 19. How many joules of heat are needed to be absorbed to increase a 14.68 gram sample of calcium carbonate from 26.3 Celsius to 36.8 Celsius? Gives you specific heat. So specific heat is telling me, all right, well, if I want to know my joules of heat, that's going to be Q equals the mass of the stuff times the specific heat of the stuff times the change in temperature, right? So this is Q equals MC delta T, sometimes called MCAT, because that kind of looks like an A, but you know, MC delta T kind of rolls off your tongue anyway. So let's figure it out. Well, the mass is this 14.68 grams, so 14.68 grams times the specific heat, which is this little c, which they tell me is 0.82 joules per gram Kelvin. So 0.82 joules per gram Kelvin. Wait a minute, Mr. Donahue, I thought you said in the previous unit it was degrees Celsius. Well, the reason for that is if I change 1 degree Celsius, it's equal to a change in 1 Kelvin, because they use the same increments. It's like saying, you know, we had this ruler, and Celsius is kind of like, I'm going to say 0 is right here, right? And that's for Celsius. Kelvin's like, whoa, why don't we go to the bottom of the ruler and actually call that 0? So the increment distance is the same, so they're used interchangeably when you talk about changes in temperature. So the specific heat for this one's 0.82 joules per gram Kelvin, same thing, and then times the delta T. So delta T for this one's going to be the final, which is at 36.8 degrees Celsius minus the initial of 26.3 degrees Celsius. And when you plug and chug that answer, you get 130 joules. Really, you get 126.3948 joules, But if you take a look, hey, we only have 2 sig figs in this number, and when you do this math, you end up with a change in temperature of 10.5, which has 3 sig figs, so you got to round it to 2 sig figs, so you're all right, 1, 2, look over, that's a 6, so that 2 is going to go up to become a 3. Cool. 20. What is the final temperature of a 125 gram sample of calcium carbonate that absorbed 67.8 joules of heat at 22.5 degrees Celsius? So they are looking for the T final. Well, I know that the delta T equals T final minus T initial. So I'm probably going to want to figure out delta T from this equation. Q equals MC delta T. So I'm going to be smart and rearrange everything first to get delta T by itself. So delta T equals Q over MC. So let me take a look. It says the specific heat, again, is we want Q first. So what is Q? It says absorbs 67.8 joules. So that's going to be my Q, 67.8 joules divided by the mass. They tell me is a 125 gram sample of it. So 125 times the specific heat of 0.82. And when I do that, I get a delta T of 0.66 degrees Celsius. So now I got to go, all right, well, am I going to go up in temperature or am I going to go down in temperature? Well, it says it absorbed the heat, so it's going to get hotter. So it wants the final temperature after absorbing heat, so we're going to go up. So we start with our initial of 22.5 degrees Celsius, and we're going to add 0.66 degrees Celsius to it because it's absorbing that heat. So I end up with 23.16 degrees Celsius. And if I'm rounding, again, I got to go, hey, it's only precise to the first decimal place, the 10th place. So I go, hey, that 6 is going to make this round up to become 23.2 degrees Celsius. There you go. That's how you do it. 21. The addition of 47.6 joules of energy to a sample of calcium carbonate raises the temperature 1.08 degrees Celsius. What is the mass of calcium carbonate in the sample? So again, we're going to be using this equation, Q equals mc delta T, but this time it's asking for the mass. So why don't I rearrange that first? So I get mass equals Q over C delta T. So now let me plug things in. Q is at 47.6 joules that they told you in the first sentence of energy over C, which is still 0.82 because we're using the same substance. So that's joules per gram Kelvin times by the change in temperature of 1.08 degrees Celsius. And we get a mass of 54 grams. Or it was 53.74, but again, 2 sig figs, which is our limiting number right there. So this rounds to 54 grams. Cool. 22. The density of liquid bromine is 3.12 grams per milliliter and has a specific heat of 0.226 joules per gram Kelvin. How much heat is needed? So again, now it's asking for Q. How much heat is needed to raise the temperature of 8 milliliters of bromine from 26 to 27.8. So again, I'm going to do some quick math right now. That tells me my delta T is going to be that 1.80 degrees Celsius because it went from 26 to 27.8. All right, well, again, I'm going to need this Q equals mc delta T. And what are they asking for this time? Q, so I don't have to really rearrange anything. But they are giving me a volume, and they gave me a density. I need it to be mass. So I'm going to have to first figure out the mass. Well, I know density equals mass over volume. So mass is going to equal the density times the volume. So mass is going to equal the density, which is given to be 3.12 grams per milliliter, times the volume of 8.00 milliliters, and I end up with a mass of 24.96 grams. So now it's going to be Q equals 24.96 grams times the specific heat, which they tell me is 0.226 joules per gram Kelvin, times by the change in temperature of 1.80 degrees Celsius or Kelvin, and I end up with 10.15 joules, which is, I'm going to have to round to just 2 sig figs because of, oh, no I don't, 3 sig figs, right? Yeah, awesome. So I go 1, 2, 3, I'm going to keep that place, I'm going to look over that 5, makes it a 10.2 joules. Cool, one more I believe in this section, and then we're done. So it says the combustion of titanium produces titanium dioxide. There's the equation. It says when 4.081 grams of titanium is combusted in a bomb calorimeter with a heat capacity of 9.84 kilojoules per Kelvin, the temperature of the calorimeter increases from 24.70 to 98.60. What is the molar heat of combustion for titanium by this reaction? That means what is the delta H in terms of kilojoules per mole? That is the molar heat. That's where the mole part comes from. It's per mole. So first, and you go, all right, well, how do I get kilojoules? Kilojoules is going to be pretty straightforward. Again, bomb calorimeter, we're talking about the whole system. It's going to be that big C times the delta T. And the moles, we're going to have to get from the grams, right? Moles equals grams over GFM. Struggling. So let's start doing this stuff. All right, so Q equals C, which is at 9.84 kilojoules per Kelvin, times by the delta T, which would be that 98.60 minus 24.70. And when I do that math, the delta T is really 73.90, so I multiply that together and I get 7.176 kilojoules. And now my moles. I go, all right, well, that was for 4.081 grams of it. What is the GFM of titanium? So I have to just look it up. Titanium is 47.87 grams per mole, which means that I end up with 0.08525 moles. So now if I want kilojoules per mole, I just do that. So delta H equals kilojoules of 727.176 kilojoules divided by 0.08525 moles. And I end up with a number of 8530 kilojoules. Now, notice how the temperature started low, ended high. That tells me that it's releasing energy, which means that my delta H is going to be a negative value. It's exothermic. So there is my ass off. Hope you found that helpful. I'll see you in class. Okay, bye.